quite recent papers, but most of the things that I have to say connect to an earlier work of mine and work of some of you in the audience. And also, I have many slides, even though, please ask questions whenever you feel. I think it's going to be much nicer if this is an interactive talk rather than just a lecture. So the motivation for me to work on the things I'm going to tell you about is studying studying thermalization dynamics of closed quantum systems is a significant theoretical challenge, and I come from the field of high energy physics, and for this field the biggest motivations certainly are alternate nuclear collisions at RIC and LHC that form a collective phase of QCD. That we know from the lattice simulations of strong interactions, although like entirely in far from equilibrium setup or non-equilibrium setup. So in order to understand how you could possibly recover an equilibrium phase in this setup, you have to understand the story of thermalization dynamics, and that was the driving force for many of the developments that I have to tell you about. But of course, in parallel, and it turns out that it's going to be also directly relevant for my talk, there's been also ultra-cold atom experiments that are capable of probing some of the phenomena that you theoretically expect to occur at high energies in a tabletop setting. What I want to stress is that the theory targets specific parametric regimes. In particular, what I have in mind is strong or weak coupling, and these two regimes have their own languages that do not necessarily talk with each other very much, in a sense that for weak coupling you have the language of, say, kinetic theory that is a language of Boltzmann equation, distribution functions, collision kernels, etc. Whereas for strong coupling you have the language of holography, which uses higher dimensional metrics, Einstein's equations, black holes, etc. So you see, like, these two languages are quite different from each other, and as a result, like, developments for weak couplings, developments for strong couplings occurred in a sense in parallel. And as a result of this, there is a possibility of drawing interesting connections between these two lines of developments in such a way that there is a cross-fertilization of ideas between these two fields. And this is basically what I'm going to talk about today. So an important ingredient of my talk is this attractor's view on QCD thermalization. So as I said, I'm a high energy theorist. So for me, the key motivation was trying to understand what happens in ultra-low nuclear collisions at RIC and LHC. So this is the artist's vision of such a collision. And the important point that I want to emphasize is that current theoretical understanding is based on sort of two attractor phenomena. One is occurring at later times after the collision. So this is the pre-collision part, this is the after collision part. And the one that is here is sort of like easier to comprehend. It's called the dynamic attractor, and it's basically relativistic fluid mechanics on steroids. So that's something that is not so exotic. A phenomenon that is much more exotic that's going to play a significant role in my talk is the so-called non-thermal attractor that occurs at least in very weakly coupled models of the collision at very early times, and it is characterized by the property of the system that the time evolution is self-similar in time. That is, if we know the snapshot of the system at a given instance of time, we can predict the behavior of the system at some range of later times simply by rescalings. And of course, in this talk, I want to facilitate connections between this bit and that bit in this cross-fertilization spirit. So let's start with non-thermal fixed points. So it turns out that if you look at the QCD physics, what you're going to conclude is that at asymptotically high energies superseding these that are reached at accelerator experiments on Earth, so like in some sense like some sort of science fiction energies, the initial state after the collision is going to be very overoccupied. That is, we're going to get a distribution of gluons of one of the particles of BCD, a distribution that is dominated by gluons, in which the number of gluonic particles at a given energy or at a given momentum is going to be way, way bigger than it would be in equilibrium. And what people have done in the course of the past 25 years is to understand that when you start with such a overoccupied distribution function, after some time, this distribution function that normally would be a function of time, obviously, as well as the momenta that exist in your system, will start undergoing self-similar evolution, in which instead of it being a function of 3 arguments, it's going to be a function of 2 arguments and a time-dependent amplitude, in which everything scales in time with some well-determined scaling exponents, right? I will try to explain how this kind of a behavior originates from the dynamics. Here I'm just sort of setting it as a say, theoretical or phenomenological observation that you can make if you have a capacity to simulate the system ab initio using kinetic theory or something like this.
So kinetic theory is the main input to derive this?
There are two ways of dealing with it. One are basically simulations of strong classical fields. And it turns out that in 2013, this was like sort of the driving force of the development in this area. And the outcome of these simulations done in 2013 is confirmation that indeed like such a self-similar regime is gonna originate. And then later, 5 years later, there was a corresponding simulation using kinetic theory. I'm not sure you should put much weight into the time separation of these days. It's largely accidental, sort of confirming largely these predictions. So like it's either classical fields or kinetic theory. These two do not have like a full overlap in the regime of validity, but there is like some overlap, and when they overlap, the results qualitatively and sometimes semi-quantitatively agree.
Sorry, what is F again?
Sorry?
What is F again?
Oh, like what I show is the distribution function as a function of one of its arguments. So this is the momentum in one direction.
Distribution function.
Yeah, this is the distribution function of gluons, and what you see is that you take the snapshot of this distribution at several instances of time after some initial time that does not show regularities, and you can take these 3 snapshots at different times and map to each other simply by rescaling the amplitude and rescaling the argument with well-defined scaling exponents, right? That's the statement. Yeah.
So is Bjorken expansion important to this?
Well, great question. The problem. So what Paolo is asking is that in this simulations, an important ingredient was built in. That is that the only dependence is on the time coordinates, a particular time coordinate called the proper time. The details don't matter very much for us, but the important thing is that you might expect that there is also like dependence on other space-time coordinates that here was neglected, and how this would influence the dynamics. And I would say that to date, people have not thought about it very much because it's technically very challenging to break translational symmetry. So sort of like it was derived in this highly symmetric setting, and if it persists without symmetry, that's an interesting problem to which I would have something to add later in my talk using some effective model well in the spirit of this conference. Yeah.
The exponents alpha and beta are understood why they have these particular values?
I will talk about it, yeah. I will talk about it in a simpler setting. So what I want to understand, what I want to present is how these non-terminal fixed points originate, where do they come from, and for this you might wonder if this setup of nuclear collision is sort of the essential ingredient. And the reason why it's already quite complicated is that this system has a special anisotropy built in the sense that when you have a collision, there's a collision axis that is one direction, and then there are all the other, 2 remaining directions. And the system is not isotropic in the sense that the collision axis is preferred with respect to the other 2. And it turns out that this is an overcomplication, and you can get rid of this overcomplication by considering systems that are simply isotropic. So in this talk, whatever I'm going to tell you, I will explain in the system that does not originate from a collision. It's a system that lives in Minkowski space, because I will be mostly talking about relativistic systems. And the dynamics only is going to exhibit dependence on the time variable, on the standard lab frame Minkowski time variable. The distribution function is going to be the distribution function that depends on time, and the magnitude of the momentum. System is isotropic, so there is only one quantity to consider. And then in such a setting, when you consider a non-terminal fixed point, it turns out that, well, I mean, it's easy to anticipate. We have a function of two variables, time and momentum, and non-terminal fixed point is going to occur when we're going to get this factorized form with the amplitude exhibiting power law, and the argument of the other function also exhibiting parallel dependence on time. So what I will tell you later in the talk is how to get this alpha and beta from the Boltzmann equation. And then a similar argument can be generalized to the work and flow, and then have sort of complete picture underlying the current state of the art. Yeah. So without dwelling for now in the details, these isotropic non-terminal fixed points come from the assumption that we have a weak coupling in the system, and our initial state is overoccupied. So we're going to start with a state that over some range of particle momenta is going to have many more particles than you would expect to have in equilibrium. Of course, at a price that perhaps like in the UV you have much less particles, at least initially when you have in equilibrium or elsewhere in momenta space. And the outcome, in particular the outcome of a simulation, you take such a distribution function, you plug it to the Boltzmann equation and run it and see what comes out. As well as experiments, in particular cold atom experiments, show that the result of this is going to be precisely the scaling, right?
Does the quantum statistics matter in this situation?
Let's come back to this issue later, okay?
I mean, they have to be bosons to be overoccupied, right?
I didn't hear what you said. Sorry.
They have to be bosons to be overoccupied, right?
Yeah, you have to take good. You have to you have to take bosons because otherwise fermions, like there can be only one or zero fermions. So also only bosons have the capacity to be overoccupied. But then when it comes to the Boltzmann equation, we're going to be taking Boltzmann equation that originate from quantum dynamics. Yeah. So this is my comment. So I guess like.
Can you say again what is definition of overoccupied?
I have Boltzmann equation. I take the distribution function like as an initial condition. I can take equilibrium distribution function, and then it's not going to evolve in time because it's like stationary point of the equation. But what I can do is I can take, at a fixed energy density, I can take a distribution function that is localized over some range of momenta. And in this range of momenta, I'm going to have a number of particles at any given momentum in this range that's going to be bigger than in equilibrium. So that's my definition. And now there's like a little observation that I want to make that is kind of obvious to anyone working with critical phenomena, but I don't think it was obvious to the people who introduced non-terminal fixed points about 20, 25 years ago. And it is the following. So these non-terminal fixed points are about self-similar dynamics, but then when you look at the plots that people make and like simulations that people make, there's like this notion of time appearing here, right? And at this time, when we have a self-similar phenomenon, then the self-similar phenomenon have special points, right? That is points that are, sort of fixed points of the scaling, right? So when alpha and beta are positive, then there are going to be two fixed points. One when t equals 0, the other one when t goes to infinity, right? These points are mapped, 1, 1 under these scalings, right? Like they don't change. When alpha and beta are negative, then t equals 0 is mapped to t going to infinity and vice versa, right? But on the other hand, the t that people use when, like they've been constructing the non-terminal fixed point or trying to describe non-terminal fixed point is some t where, like the t equals 0 is, I don't know, like the time they started experiment or the time, like when they arbitrary date, right? So there's like some arbitrariness in how you choose the origin of time here, whereas like similar phenomena have this feature that sort of the origin of time matters for them, right? So there's some tension here, and I want you to keep in mind this tension, and I'm going to come back to this tension, how to resolve it later on in my talk. Good. So this is how I wanted to introduce non-thermal fixed point, and then I will try to explain where they come from. But for the moment, I want to come back to this near equilibrium setting, something that I think we as a high energy physics community understand much better. And in this setting, I want to talk about quasi-normal mode phenomena. So what a quasi-normal mode is, and many of you know it, but I want to go through all the steps in some pedagogical detail. So let's imagine that we consider a wave equation in a cavity. So a wave equation is like just D'Alembertian, and then what we're gonna, the cavity means here that at the boundary this field whose wave equation, which solves the wave equation, vanishes at the boundaries of the region. And then when we deal with such a problem as undergrad students, what we discover and what people discovered probably in the 18th century is that there is a spectrum of normal modes in the problem, maybe 19th century. Which is that when we solve this equation in Fourier space, and we can solve it because the system is translationally invariant in time, and we assume that it's going to be spatially homogeneous, what we see is a set of normal frequencies, I mean real frequencies, that are here enumerated by some natural number that we get. And then if we excite such a system, like a guitar string, for example, what's going to happen in the idealized situations without any friction is that this system is just going to have oscillations of these normal modes. And the interesting patterns that we get, in particular, interesting musical effects we get from interfering these normal modes with each other, right? So that's the picture of normal modes. And the quasi-normal mode that this talk is largely after is a situation in which we also get the eigenspectrum, the eigenfrequencies in the problem, but these eigenfrequencies come out complex. They have both real part, as we already seen for normal modes, but they also acquire imaginary part that is responsible for dissipation, for the decay of the amplitude of such a mode. And then there are two ways that at least I could think of obtaining quasi-normal modes. Perhaps there are others, but these are like the two ways that are relevant for this talk. One way of obtaining such normal modes is if the equation breaks time symmetry explicitly. And one paradigmatic example that's relevant is the diffusion equation, right? This equation only has like first derivative in time. Again, when we consider this equation, say, on a line, but it doesn't really matter very much at this level of the discussion, then we introduce the spatial momentum into the problem. And then when we seek for the frequencies omega, I mean, like it's a trivial problem, we solve this equation, and what we get is we get a frequency that is purely imaginary, and it corresponds to an amplitude of the signal that is decaying in time, right? And this occurs because the equation breaks time reversal symmetry explicitly. The other option is that perhaps the equations do not break time reversal symmetry explicitly, but actually the boundary condition that they have makes the problem non-Hermitian and leads to the appearance of multi-frequencies. And a paradigmatic example for me, but there are many examples in the literature, is a black hole. And a black hole is at least at the classical level, is a perfect absorber in the sense that nothing can ever escape a classical black hole, I mean, as predicted by general relativity. And as a result, like when you solve for a behavior of a field outside the black hole, what you impose is a condition is that this field is ingoing at the horizon, and this condition breaks the symmetry when we reverse time, and as a result, the frequencies come out complex. And now the interesting thing that applies to both situations is that if excited, quasi-normal modes decay in time. Their amplitude gets smaller as time progresses, and this very beautifully encodes dissipation in the system. I mean, like the ability of the system to return, I mean, to come back to the equilibrium configuration, to the say, homogeneous configuration in most cases, right? What I want to emphasize is that these quasinormal modes often contain both real and imaginary parts, and whereas like this imaginary part is responsible for the decay, the real part is responsible for oscillation. So we have both interference as well as the decay. And now, if we go to holographies, and holography is a way of describing strongly coupled systems in terms of higher dimensional equations for gravity. The details don't matter for this talk. It's a well-established technology, but if you go back, for example, to the paper that Pavel and Andris Starinas wrote already 20 years ago, time is flying. You can consider perturbations of gravity on top of a black hole in 5 dimensions. So that corresponds to the properties of how energy momentum tensor operator evolves in 3+1 dimensional strongly coupled quantum field theories, relativistic quantum field theories. It turns out that this is the spectrum of the quasinormal mode frequencies that you get. So the spectrum is going to be a function of the spatial momentum. So we introduce the spatial momentum into the problem. And the spectrum changes as a function of the spatial momentum, and that's going to play some role in the discussion soon after this slide. But the point that I want to make is that the spectrum has this beautiful Christmas tree structure in which vast majority of the modes have a decay rate set by the temperature of the system, which is these excitations are going to be very quickly, exponentially fast in time dumped from the dynamics of your system. And there are lots of them because the spectrum continues all the way to infinity over here. But then there are a few, literally a few, long-lived perturbations that are associated with high dynamic degrees of freedom. And these are the perturbations with a property that as spatial momentum goes to 0, the frequency associated with these perturbations goes to 0. Which means that by making spatial momentum arbitrarily small, we can make their decay rate arbitrarily small. And as a result, we can let them survive for arbitrarily long time scales.
So, excuse me. So yes. Do you have the case that we have the branch cut rather than the whole?
That's an excellent question. So this is the story of holography. And in holographic models that we have under full control, the structure is roughly like this in a physically interesting number of dimensions. Now, if you look at kinetic theory, so if you try to do this exercise in kinetic theory, this hasn't been done in full generality. It only has been done in a handful of models. And there, what you see is that these singularities, some of these singularities, this transient decaying sector can be turned to a branch cut. Yeah.
Sorry, maybe more basic part thing. So did you say that they go to the real axis in a certain limit?
Yes. So what I'm saying is that when you take the spatial momentum, I'm showing on this screen. When you take spatial momentum to 0, these two blue modes that correspond actually to high dynamic sound waves go to the origin. The reason for it is that their frequency is proportional to Q. So when Q goes to 0, they go to 0, right? But the other things, the other excitations in this limit stay gapped. As a result, they are exponentially decaying in time. Yep. So now we transition to relativistic high dynamics. So the reason why these two modes are, in this example, protected from becoming gapped are conservation equations. They arise for perturbations that are associated with the energy momentum tensor, and energy momentum tensor is a conserved current, conserved tensor. And we can explain the properties of these quasinormal modes in terms of relativistic Navier-Stokes equations, in the sense that if you take relativistic Navier-Stokes equations, plug there the ansatz for small perturbations, what you're going to see is that such frequencies are going to obey order by order in the small momentum expansion this relation, and then it is indeed reproduces the behavior that you obtain ab initio from holography, in a sense that you get the value of the speed of sound. Here, in this case, considered by sound, the speed of sound is 1 over square root of 3, because the system is conformal. You also get the shear viscosity. The shear viscosity that you get has a property that is 1 over 4 pi times the entropy density. And you can keep going and obtain terms that have cubic and higher orders in a systematic manner. And of course, like, what I want to stress is that this shear viscosity describes the dominant dissipative effect in the system. And of course, when you look at this, and you've seen this part about non-terminal fixed point, the question that might arise is, okay, these are sound waves propagating on top of equilibrium system. If you have a non-terminal fixed point, can you have sound waves that propagate around it? And this connects with Paolo's question related to the fact if you can get a non-terminal fixed point in the case of broken translational symmetry, right? If you have sound waves on it, then the answer to this is yes. And there's one thing that I want to say that connects to what Luca has been interested in for most of his career, is that in this talk, I will be considering systems without fluctuations. So the special relation that we consider here have only integer powers of q, and of course, including the effect of fluctuations on these kind of properties of the system is one of the active fields of research where some lessons have been learned, but I would argue that a comprehensive picture still awaits.
What is a relativistic Navier-Stokes?
Relativistic.
Okay.
Yeah, relativistic Navier-Stokes is a statement that we have a energy momentum tensor that is an operator that has 10 independent components, if you think about it in grand terms. And basically, relativistic Navier-Stokes originates from saying that these 10 different components of the energy momentum tensor are expressed in terms of fluid dynamical variables, which is velocity and, say, temperature, and their derivatives, right? And when you do this in a systematic manner, you get equations that are relativistic generalizations of Navier-Stokes.
It doesn't break relativistic invariance.
Yeah, it's relativistic covariant. Covariant, of course, you might say, okay, the thermal state breaks relativistic invariance because it sets the preferred sort of rest frame of your fluid. Yeah, but it's sort of always like this. So yeah, and there's like this is like a vast body of literature, so I'm happy to discuss it after.
Yeah, no, sorry, I understood that you.
And I hope like this addressed your question to some degree. And of course, you can wonder like if this is something that generalizes in the presence of nonlinear effects, and the answer is yes. So over here, what you see is a result of ab initio simulation of the quantum field theories and Strominger-Kaplan quantum field theory. And in particular, you see that there is some universality emerging at late times, and this universality is precisely the viscous tail associated with Navier-Stokes equations. And then like there are some transient effects appearing beforehand. And these transient effects, if you do some data analysis on this, are going to be precisely exponentially decaying with the frequency that is dictated by the gap in the previous plot, right? So this is all very nice and physically important. And before I move on to the non-terminal fixed point, what I want to say is that in the course of the past 20 years, I would say that quasi-normal modes appeared as an organizing principle for understanding near equilibrium phenomena in holography, but also to some degree in theory. And in order to give you a bit of a snapshot of what's going on, let's consider a small excursion. So this bit, what I'm showing here, is a relativistic generalization of the diffusion equation, right? So the diffusion equation, it turns out that it arises from looking at relativistic Navier-Stokes equations, and this sort of equation, the telegrapher's equation, is a natural generalization of the diffusion equation to account for relativistic causality. So what you see here on this slide is a diffusion equation plus a term that is a second order derivative in time. So when you look at this equation with 3 terms, you can group these terms in pairs, and when you group these two, you see a diffusion equation. But when you group like this one and that one that are denoted in green, you see a wave equation. So this telegrapher's equation is an equation that, in some functional sense, interpolates between diffusion and wave propagation. And as a result, because it includes wave propagation, there is a chance of making this equation causal in the sense that the signal propagates inside the future light cone. And the beautiful thing about this thing is that the equation is second order in time. So when we seek for the quasi-normal modes associated with this equation, it's a simple undergrad or even high school exercise. What you're going to do is you're going to find two solutions, right? There are two time derivatives. So you get 2 powers of omega originating from this equation. And these are the solutions. And now what you can do is you can plot these solutions in the complex frequency plane as a function of the spatial momentum. And what you're going to see, and this demonstrates a very beautiful finding first by Ben Witters and later corroborated by Pau and collaborators with many other developments to follow, that when we think about quasi-normal modes, and we think about their momentum dependence, and more generally about dependence on any continuous parameter, what these modes do is that they dance on the complex frequency plane, and there's going to be some particular values of the momentum, possibly complex, where these modes are going to undergo collisions. And this is precisely what you see here. So we start at very small value of the momentum. There is a diffusive mode that lies very close to the origin, and there is a transient mode that lies close to inverse of the parameter called relaxation time. But then we increase the momentum, and here we can just consider spatial momentum. These two modes are going to meet at a particular point in the complex plane, where these two frequencies are going to perfectly coincide. And then when we keep increasing the momentum further, what's going to happen is that after this collision, these two modes are going to be repelled from each other in the other direction, and then they're going to move parallel to the real axis. So this kind of a behavior that we see here corresponds to the diffusion, but this kind of a behavior that we see here corresponds to propagation. And this really encapsulates this property of the telegrapher's equation that it interpolates between diffusion and propagation. But the crucial thing here is that there is this well-defined scale in this particular model associated with the collision between the high dynamic mode and the transient mode, and more generally between any of the pairwisely quasi-normal modes that exist in the system. And it turns out that the fact that the modes collide and the fact that there is like this radius associated with the collision, this plays profound role in the discussion. In particular, if you look at these dispersion relations in the simple model, what you see is that the value of the momentum when the modes collide, so this R, is precisely what sets the radius of convergence for small momentum expansion of these dispersion relations, right? So in particular, what you see from the simple model is that the derivative expansion, so high dynamic derivative expansion, is going to have a radius of convergence that is associated with the presence of other excitations in the system, right? So that the fact that there are other excitations in the system makes high dynamic derivative expansion not to converge everywhere on the complex momentum plane, but also only to have a finite radius of convergence. It turns out that this is
Excuse me?
Yeah.
So this kind of behavior is rather common in non-Hermitian physics, right? Is it somehow related?
It's not something that originates only here. I mean, I've seen it in multiple other examples. Yes. So there are possibilities of further transfer of knowledge between this and other fields.
For the case where two points merge, people talk about exceptional point or something like that.
Yeah, it's called in other part of the literature exceptional point. Indeed, it's also possible to have collision. So the fact that this collision is between two modes is associated with the fact that the singularity over here is a square root. But you may also imagine that you have for example, a cubic root singularity, and that would correspond to the collision of 3 modes. And I think it's not excluded. I think there's been even examples in the literature where people have seen it.
It's sort of the transition from underdamped to overdamped oscillator, right?
It's possible. It's possibly the case. Yeah. But the point here is not to get too much attached to this equation. It's just a simple way of illustrating a more general phenomenon that was observed in a much more complicated setups. Yeah. Because indeed, like if you look at, and here I'm just going to be sketchy. If you look at the consequences of this picture more broadly, it turns out that you can show that causality and dissipation dictates that this radius of convergence is going to be finite. And then, based on observations in various models in the absence of statistical fluctuations, we see that this radius of convergence actually, in most cases, is bigger than 0. Like, I only know one example without fluctuations where it's 0, but generically, in holography, it's bigger than 0. And now what you can do is you can use this information to show that if you look at the real space properties of the system, then generically what you expect is that the derivative expansion associated with relativistic dynamics is going to be factorially divergent. So that like this finite radius of convergence over here, finite radius of convergence over here is going to translate to a 0 radius of convergence in real space. You can show it.
So this is the Hadoop expansion of the linearized Hadoop dynamics.
Yes, okay, that's it.
Everything depends on the state.
So over here, this is at the level, you can show it at the level of linear response theory quite generically, but you can also take nonlinear derivative expansion, and I can give you, I can show you the results later on, where you see the same phenomenon, that is factorial divergence. So this is nonlinear dynamics of nuclear collisions, for example, you see it. Yeah.
So you see this asymptotic series.
Exactly. And now, like, if you have like this factorially divergent dynamic expansion, if you start asking questions about all order dynamics, so like trying to resum derivative expansion to account for strong dissipation, it turns out that if you think about it, and this is what we did with Michał Spaniński in 2015, that there doesn't seem to be a definition of all order resum dynamics from within. That is like without invoking some physical elements that sort of supersede the derivative expansion itself. And this led us to propose this notion of dynamic attractors. And that's like sort of like another place to go, where I don't want to go now. And then like there's something that I find very, very, very aesthetically pleasing, in a sense that you can sort of put various things together and show that that causality actually not only implies that you have like this finite radius of convergence, but also it implies that there are bounds on transport coefficients in relativistic fluids. And it turns out that it predicts that these transport coefficients cannot live anywhere in this abstract space of transport coefficients, but there is like some convex shape that is the landscape of relativistic transport that we called hydrohedron in a paper 2 years ago. So the punchline from this snapshot is that there's a very attractive picture of near equilibrium behavior associated with quasi-normal modes. So as a result, it's an interesting question if this picture generalizes anywhere else. In particular, if it generalizes far from equilibrium to the setting of non-thermal fixed points. And this is what I want to do in the rest of the talk. Any questions about near equilibrium still?
So I guess, I mean, bridging to, you talked about weak coupling versus strong coupling. This was mostly a strong coupling picture?
Well, this was mostly strong coupling picture, although
pole collision hasn't been observed in with kinetic theory. Is there other examples of?
So in kinetic theory, I think this picture is only understood in several simple models that all stem from the relaxation time approximation to the collision kernel. What happens more generally, I mean, there are singular papers, and like literally a few one or two papers that try to do something, and I think it's like one of the interesting places to go. But what I want to do is I want to go to kinetic theory far from equilibrium and try to see it. Yes?
So you show that the collision of the two damping hole to make it to the propagating mode.
Yes.
And do you have such behavior in the holographic model?
In holography, I think the picture is more intricate. I mean, like maybe Paolo remembers the details, but I think the picture is more intricate.
I can show you lots in my talk.
Yeah. Okay. Yeah. But the sort of like the philosophy is very similar. So that you cannot have, the idea is basically you cannot have diffusive behavior forever because diffusion badly violates causality. So what you do is you collide with something to give rise to a behavior that is permitted by causality. Yeah. Good. So let's talk about the setup. So from now on, we're going to be exclusively using isotropic kinetic theory. So we're going to have first derivative acting on the distribution function that is isotropic, and the evolution is going to be governed by some particular collision kernel. One example of the collision kernel that we're going to consider is a Fokker-Planck QCD collision kernel, but that's just, like for definiteness. The story that I have to say is more general than this. And when you run the crank, you're going to conclude that if you have this kind of a collision kernel, the non-terminal fixed point that you're going to be describing with this kernel corresponds to a direct cascade to the UV. That is like the characteristic momentum in the system is going to be in a power law manner shifted to the ultraviolet, to high momentum, high energies.
I mean, in QCD, there's no thermal mass, so why should we trust perturbation theory at high temperatures?
Well, I mean, I'm not sure. I mean, the kernel that you really consider and apply to QCD is a much more complicated kernel. I mean, like this kernel only corresponds to the 2-to-2 scattering, regularized in the IR by the thermal mass associated with the system.
Okay, so you are putting in some carefully selected non-perturbative effects.
Exactly. I mean, this is the story of this Arnold Moore-Jaffe kinetic theory of QCD. It's a very intricate, complicated story. But for practical purposes for us, is that this is one simple, relatively simple example of the collision kernel that has this nice property that because of the limits that are taken, there are not too many integrals left to be evaluated, which is a very significant technical advantage. That's the point.
Is there one question about this kinetic equation? I mean, usually, at least in the non-relativistic context, what I'm used to is that you actually have a cubic nonlinearity rather than a quadratic nonlinearity. And so how come,
you have a cubic, you do have a cubic nonlinearity because you have F here, for example, you have F here, but this IA is quadratic in F. IA is quadratic in F, so you have 2 powers of F plus 1 power of F, so it's cubic.
No, then the last term is quartic, right?
The last term, no, because IB is linear,
okay.
F, so it's cubic. Everything is at most cubic. Yeah. So it's correct.
Okay.
Sorry, I'm confused about the notation. What's the curly L?
Oh, good. So the curly L is a leftover. So the curly R is a leftover integral that you have if you try to derive this equation from QCD, and then this term requires some particular regularization and gives rise to all sorts of trouble. But it turns out that for the purposes of this talk, this term can be treated as a perturbation in a sense that you can assume in the first order that is constant, and then try to include it systematically in a perturbative expansion. Yeah.
And sorry.
Sorry if I ask you more questions, but what is the entropy is the bosonic entropy, which sort of is increasing in time under this evolution, or?
Yeah, I mean, what I would do is I would use statistical entropy for the system.
What is the form of the entropy? I mean, is it bosonic or is it classical? I mean, it's F log F or presumably not. I mean, then it wouldn't increase, right? I mean, so it must be something like
Fermions or
1 plus F or something like that. I mean, that's precisely the one. Yeah. Okay.
Yeah, I mean, I haven't thought about it. So
Okay.
yeah, I mean, I would. Yeah, I mean, that's not gonna. I mean, what I'm assuming is that there's gonna be entropy function that's gonna be increasing under this evolution. I mean, it's not gonna play an important role in this analysis, apart from the fact that it's not going to exhibit a nice, because of the lock, it's not going to exhibit nice time dependence at late times. That's the only thing that's going to be important for the discussion. Yeah.
So, but indeed, so the statistic of F is the one of waves.
Sorry?
It's wave statistics, like radiation.
In what sense? Like, you mean bosonic, or you would say more?
Rayleigh jeans or something.
Yeah.
Rayleigh jeans, type of formula.
You're asking about the tail.
No, the I mean, the question is the same as Herbert. Like, what's the? I mean, typically, if you know the statistics, you know the entropy associated to having this distribution. I don't know if it was Fermi-Dirac, it would be F would be between 0 and 1. If it's bosonic, is
This is all out of equilibrium, right?
Yeah, it's out of the.
no, that doesn't matter, right? I mean, you need to know the statistics of the particles, right? I mean,
F is distribution of quarks.
No, F is the distribution of
Gluons, yeah, so it's bosonic.
Quarks are subleading to this picture because you cannot overoccupy them.
Yeah, so it's F times 1 plus F.
sorry,
It's bosonic. F times 1 plus F is the.
it's bosonic.
Yeah.
And F times 1 plus F is like basically F squared, right? Because F is very big.
Yeah, that's true.
Yeah, it's bosonic at high occupancy.
Yes.
So it's Rayleigh jeans.
Yeah, so the important piece of observation is that if F is significant, then if we have a general collision kernel, it's possible for this collision kernel to exhibit homogeneity as a function of the amplitude of the distribution function, and as well as homogeneity as a function of momentum. That's not guaranteed, but there are examples of kinetic theories where this occurs. That is, like, when we take F to be very big, then a rescaling of momenta or rescaling of the amplitude of the distribution function is going to just pull out a constant prefactor outside the collision kernel. And when this is the case, and this is the origin of non-terminal fixed point, what turns out is if you adopt the ansatz for the non-terminal fixed point, you can factor out time dependence from your collision kernel. That's a very non-trivial step that underlies the origin of non-terminal fixed point in the language of kinetic theory. And when we just take the highest powers of F in the collision kernel, we might still alter the conservation properties. And as a result, like, what we want to do is we want to impose conservation of energy or particle number on top of it. And when we do it, when we impose conservation of energy or conservation of particle number within the range in which overoccupation is valid, because energy and particle number might be conserved, over all momenta, then what it gives is it relates the amplitude, time-dependent amplitude of the distribution function to this t-dependent rescaling of the momentum in terms of a very simple power law with a power 4 for the conservation of energy and the power 3 for the conservation of particle number. So as a result, conservation of energy or particle number relates A and B, and as a result, like, you can just use one and the other consider as a derivative quantity, right? And now, of course, we assume overoccupation. So related to your question, from the collision kernel, for example, from the Fokker-Planck collision kernel, what we're going to take is the highest power of F. And in this case, the highest power has a power 3. And this collision kernel, as we said, leads to a direct cascade to the UV. So this is like sigma equals 4. But now, like, the beautiful thing happened is that the assumption of the overoccupation and conservation equation, what it does, it factorizes the Boltzmann equation. In a sense that the Boltzmann equation, by separation of variables, separates into equation that is a simple ODE that describes time dependence, and a more complicated integral differential equation that describes the shape of the scaling distribution function. And this is basically a derivation of a non-terminal fixed point. So we have overoccupied condition, and we we assume that the overoccupation is going to persist over some range of time, plus conservation equations. And from this and homogeneity or approximate homogeneity of the Boltzmann equation as a functional of amplitude of the distribution function and spatial momentum, we obtain the separation of variables. And as a result, we obtain an effective equation in the spirit of effective field theories for non-equilibrium physics, effective equation for the evolution of the system, and an effective equation for the shape of the distribution function, right? And we can solve these two equations separately, keeping in mind that the separation of variables constant, is common for both equations.
So why do you need to impose conservation? Couldn't you have particles flowing out of the regime where your scaling applies into either high momentum or low momentum?
You have this effect, but we assume it's a small effect. Because if we don't have it, then A and B could be different.
Right.
And I think there is a generalization to this picture in which you account for this effect that nobody bothered to see. I think the interesting question would be, is there some order? Is there some regularity when you have this effect built in? Because in experiments, I don't think this kind of effect has been seen as a significant effect. But if it's significant, it will be very interesting to try to understand, what emerges from it. Yes?
You mentioned at the beginning of the talk that you also require the interactions to be weak. Presumably this is there are higher order terms as well in that collision kernel. Presumably this is so you would have more factors of error.
Exactly. And that's a very great comment, because if you have higher order interactions, then you have higher powers of the distribution function, and then sort of overoccupation and the interaction strand, the limits don't necessarily commute with each other, right?
There's a certain order of limits.
Exactly. First you take interactions weak, and then you take overoccupation. Yes. Great comment. Thank you. Yes.
So then, like you already answered some part of it. So then it doesn't depend as much on the distribution function because it's a weakly interacting theory. Like because you're doing some kind of power expansion, and then if so the final scaling that you get seems to be, is it independent of the, like, does it just have to be overoccupied or a specific scaling?
No, if you violate overoccupation, all this argument goes out of the roof, right?
Yes, but then generally, let's say if I was doing some expansion,
yes,
I would have to know the scaling of the field, and then that would tell me when to truncate the series. So here, assume overoccupation. Is there like some scaling that you?
Good. So I'm assuming weak coupling and then overoccupation at a fixed value of the coupling.
And that always means you restrict at first order and not
Yeah, exactly. Yes. Yeah. And then what I want to emphasize is that what happened here is that we had a distribution function that was a function of two variables, and then what we do is we factorize it into a function of one variable time, amplitude, and one variable momentum, rescale momentum. Right? So that's in some. I'm not a mathematician, but in some functional sense, it's a vast reduction of complexity of functions because there are sort of many more functions of two variables than there are products of function of one variable and one variable, right? Yeah. I don't know how to phrase it in a nice way mathematically. But anyway, if you look at this equation has a solution that takes this form, and then what should come back to your mind is this statement that I made earlier, is that the scaling phenomena treat the origin of the scaling argument as a special place. And what happens is that the system here offsets time in an initial condition dependent way, in such a way that this t minus t star has some well-defined notion of the origin that the system picks for itself, right? So we, in this way, from this equation, we not only derive scaling that occurs at late times, but actually we derive this offset in time that goes under a name or connects with an Elliott development that was called prescaling, which is like a scaling with a time-dependent but weakly time-dependent scaling exponent, right? But in the end, like the whole physical content is offsetting time in the initial conditions, so initial state-dependent manner, in such a way that the system picks like what it wants to call the origin of time.
So I don't think I understood why there are two time scales, the offset time and the reference time.
So one time scale comes from from this constant d1, and this is what we call tref. It's basically, this controls the amplitude of the scaling function, and the other time scale comes from solving this as a differential equation from the initial condition. And the beautiful thing about it is that Zoran Hadjibabic and collaborators in 2023, so 6 months after we introduced this, found precisely this effect in their data, in the sense that here they measure the distribution function at different values of times for the cascade to the IR here in this picture. So this is the cascade associated with the particle conservation. This cascade occurs to the IR. But after the dust settles, it turns out that you get for differential conditions, for different times, you get a single curve from your data, like without any significant spread, when you introduce this offset that is initial condition dependent. So what they did here is a confirmation of this prediction that non-terminal fixed points actually come out naturally associated with this offset, and this offset becomes irrelevant as you go to very late times because it's, in Taylor expansion, it's a subleading effect. So this is the story of the origin of non-terminal fixed points as it could have been set from the beginning with a connection called up experiment. But what I want to do is I want to go forward in the remaining 5 minutes. I want to tell you about trying to frame this picture into the picture of quasi-normal modes of non-terminal fixed point. So remember, we introduced the quasi-normal modes when we had a system that is given by the background that is time translationally invariant plus the perturbation, right? And the beautiful thing about non-terminal fixed points is that there is a sense in which non-terminal fixed point, even though it's a time-dependent far from equilibrium phenomena, is static. That is, the scaling function does not change in time over a very long time until the system starts thermalizing. So if we think about doing perturbations on top of the scaling function, then the picture of eigenfrequencies should make sense because this rescale momentum is time independent and the equation effectively is time independent. And as a result, the notion of a quasi-normal mode approach should make sense. So in this picture with my PhD student Mathis Delescluze, in this paper with my PhD student Mathis Delescluze, what we did is we tried to, we took a Boltzmann equation with the general collision kernel that gives rise to non-terminal fixed point, and we tried to see what kind of quasi-normal mode approach is going to be consistent with the kinetic theory. And it turns out that the funny thing about it is that the only thing that is consistent with the equation at zero spatial momentum is a quasi-normal mode approach that gives rise to parallel behavior in time. So it turns out that this is the consequence of the equations of motion given by the Boltzmann equation. And now what we did is we took the Fokker-Planck Boltzmann equation, so a particular collision kernel, and we adopted techniques that we knew, at least I knew initially from holography, to calculate the quasi-normal modes. And the picture that emerges is this, which is that there are discrete set of quasi-normal mode frequencies that seem to continue in the sense that we have some frequencies that we obtain here, but they are numerically unstable, so we cannot really make a statement. So this is consistent with the prediction that probably there could be infinitely many of them. And there is a gap in the spectrum. There is like one gapless mode, and then all the rest are decaying modes. But they are decaying not in an exponential way as quasi-normal modes of holography decay, but they all decay in a parallel manner.
So usually quasi-normal mode is some kind of exponential I omega t. So here there's no I omega t, right?
There's I omega t. Sorry, there's I omega log t. Because what the system wants to call t, you have to let the system decide. And in holography, the system decides that what's under exponent is t. Here the system wants what's under exponent is log t. It's a different system, so I let it do its own thing. Right, so what you should keep in mind is this picture. So over here, you had two modes that become gapless in the limit q going to 0. So that's consistent because we've been working with zero spatial momentum for non-terminal fixed points. And all these are transient excitations, right? And now the thing is, okay, I mean, like, this is a new prediction. People have not looked at this before. Can we do any cross-check, right? And it turns out that, yes, we can. The reason being that the background state, the state on which we expand, has two parameters. One is what I previously called Tref. Here it's like T0. Sorry for the change of notation. I forgot again to change it. And the other one is this T star, this time-dependent offset. So when we have like two parameters in our background, we can consider their variations. And these variations should be thought of as quasi-normal modes themselves. And it turns out that when you do a linearization, in Tref, so in this T naught, you reproduce the gapless mode. And when you do a linearization in T star, you reproduce this mode that is here at -1. And you see here the shape of the mode in rescaled momentum overlaid the prediction of the series expansion, the parameter, as well as numerical prediction of the derivation. And you see that in both cases, the agreement is exceptionally good, right? So like that's a notional confirmation that we are on the right track onto something.
Sorry, I mean, isn't this how you derived it? Or
No. What we do is like we consider the quasi-normal mode spectrum for the Boltzmann equation, and we represented it as a one big matrix, and we diagonalized this matrix. And
but the Boltzmann equation also gave you this solution, which
but
has these parameters.
Exactly, the Boltzmann equation also gave us the solution.
Right.
So
it's a consistency check.
It's a consistency check. Yeah, it's a consistency check. Yeah, but it better works, right? Than in one case.
But the input is the same for both. It's the Boltzmann
yes,
equation.
it's the Boltzmann equation. Yeah, of course. And then of course you can think about it. You know, this thing over here -1 corresponds to variations in T star, and variations in T star is nothing else than this prescaling. So you might think that this quasi-normal mode at -1 or -I, more precisely, is precisely what's been observed in the experiment, right? Like that's the explanation of the experiment. And then what we claim is that there are many other quasi-normal modes that the experiment in principle can see. There is something that is quite puzzling here, which is that between this -I mode and the gapless mode, we see two other modes. And the question is like, you know, is there something that should be even stronger effect? I mean, longer staying effect than the prescaling? It seems, our study seems to indicate that yes, but a more thorough understanding would require, you know, going through different examples. So anyway, I'm running out of time, so I just want to make a quick statement that, you know, in the context of holography, the hydrodynamic excitations arise from the gapless mode at zero spatial momentum. So what you expect is that when you introduce spatial momentum into the problem, what we call the gapless mode splits into hydrodynamic modes. And in a recent paper with Jürgen Berges, Gabriel Denico, and Timo Price, we confirmed using an approximate way of solving Boltzmann equation, that this is indeed the case, that non-terminal fixed points can be characterized by a diffusion around the non-terminal fixed point, as well as hydrodynamic sound waves propagating around non-terminal fixed points, with an interesting outcome that the shear viscosity that one obtains from the setting is intrinsically time dependent. That it's not like it's a far from equilibrium phenomena, so the shear viscosity is not like in equilibrium a constant or something given in terms of thermodynamic parameters, but it's something that is intrinsically time dependent. So that's a very good place to close the talk by just re-saying what I said earlier. The first development that I described is trying to go back to the origin, how non-terminal fixed points emerge from the Boltzmann equation. And the interesting observation of this is that there is an initial condition-dependent offset in the scaling that connects with an earlier discussion that I didn't cover today of what people called prescaling. The other development that I discussed that is more recent from earlier this year is that you can think about the emergence of a non-terminal fixed point as originating from the decay of transient quasi-normal modes around them. So this neatly connects with the discussion of thermalization at strong coupling in holography, and that, you know, if you add the spatial momentum, so these two developments do not have any inhomogeneity in them, but if you add spatial momentum, this reveals hydrodynamic excitations around non-terminal fixed points and opens, related to Pavel's question, a window on sudden inhomogeneous non-terminal fixed points. Similarly, in which, you know, the nuclear dynamics, the relative nuclear dynamics in nuclear collisions is inhomogeneous. So of course, only this development has been confirmed by the experiment. I mean, like this only partly for the trivial mode. So there's like a lot of you know, interesting open questions in which I hope I convince you are worth pursuing. pursuing. Thank you.
Okay, so we already had a bunch of questions, but are there maybe one or two final ones?
But so in the experiment of that you cited,
yes,
in that case, they always have a forcing and a dissipation, right? I mean, that's how they get the non-thermal steady state, right? This cascade regime is with forcing. I mean,
no, I don't think it is. This one, I think, is like they create a state that is overoccupied, and as far as I understood, like from them, this is sort of the main challenge for them, what kind of a quench to do to create the overoccupied state, and then just let the system evolve with constant interaction. This is my understanding.
okay, maybe I don't know this one, but I mean,
but also non-thermal fixed points do not. I mean, non-thermal fixed points are about isolated system dynamics, so you don't want to have forcing, right? So like you don't.
All these wave turbulence thing, they always have. Of course, it's isolated, but there is forcing. Like they squash the system.
No. Okay, that's an excellent point. So over here, these non-thermal fixed points arise from taking an overoccupied initial state and having a transient regime in which system is self-similar. But it's not that you pump particles or energy at one end and try to develop something that is quasi-stationary. Here, you develop something that is scaling but transient. For example, the cascade that I was talking about, the UV cascade, has a property that the amplitude of F drops with time. So at some point, the system thermalizes because you cannot make this assumption anymore that only highest powers of F dominate.
Right, so this is not stable. Okay.
No,
so
it's not stable. No. Like this system has a finite lifetime, but I think in their case, they don't thermalize because of the, they don't thermalize because of the evolution of the system. I think they thermalize because like either the environment kicks in or like maybe like they probe already like the full box. I mean that's basically equivalent, right? So like it's not that they observe the system all the way to thermalization. They can make a full statement. I mean like they just observe the emergence of the scaling and what happens before scaling, and that's already quite exciting.
Now you had a question.
Yeah, so you said you have a mix on top of this fixed point, and I suppose it's controlled by the conserved quantities. You have conserved particles and energy, right?
Yes.
But you just have two parameters characterizing your set of fixed points, right? T0, T star, if I understand.
Yes.
Usually there's a correspondence between the number of parameters characterizing a set of states, number of conserved quantities, and then you see the slowly varying parameters as being.
So in this case, I think we have two discrete. I mean, we have one discrete parameter, which is if the fixed point is governed by the particle conservation or energy conservation. So like that's like one or the other. Once you make this choice, then the initial condition tells you like what's the value of this parameter that I was referring to as Tref. I mean, let me try to uncover it.
Essentially, what is the space of possible values of conserved quantities you'd have in your set of states?
Yeah. So you have one of two conserved quantities, and then the question is, what is the total particle number in the system, because it's dominated by the scaling dynamics, right? And this allows you to fix basically the amplitude of the scaling function, and this fixes for you like this constant. So that's one input, and the other input is more intricate, and I don't think it's very well understood. At least I don't understand it. Is how this T star exactly emerges. I mean, like this is related to the initial state physics, but we didn't understand it, and I don't think. No. So nothing that has been proven in the experiment is hydrodynamic. I mean, like all this stuff is about systems that are homogeneous. You can only have hydrodynamics when you introduce spatial momentum. So you have to break homogeneity, and I think this is like sort of like the next step for this studies. And so far, only theoretical step has been made. Experimental, not yet.
So maybe we can continue the discussion over. Let's think.